Okay, good morning, everyone. It's a pleasure to have Goran give a talk today. Goran has been a postdoc at ISI for the last 3 years, and before that, he obtained his PhD in electrical and computer engineering from the Technical University of Dresden in Germany. His work there was on modeling cascades of failures in power grids and coming up with mitigation strategies and techniques to make networks more robust and resilient. One has to wonder whether the people in Texas in charge of the power grid there read Goran's PhD dissertation. They would have probably be better with that. Here at ISI, Goran has been working on a variety of different projects, including some sponsored by DARPA on social network dynamics, teamwork, and science of science. And today he's going to talk about networks, human and machine behavior. And for the first 30 minutes or so, the chat is going to be disabled. After that, people will be able to use the chat to ask questions, and towards the end, during the Q&A session, some of you will be able to unmute yourself and ask questions as well. So Goran, please get started.
Thank you, Emilia. Okay. So first of all, it's a great pleasure for me that I have an opportunity actually to talk with all of you about the work that I've been doing at the ISI in the previous years. And so the time I have is limited, so I will just focus on some aspects of my research. And I hope you will get to know what I've been doing and where I intend to go with my research in the following years. So the topic of this talk is networks and behavior, and how we can model human and machine behavior in the hyperconnected world. So on Sunday, December 4th, 2016, Edgar Madison Welch, a 28-year-old man from North Carolina, arrived at Comet Pizza Shop in Washington, D.C. So he started shooting. Luckily, nobody got hurt. So what was the motive of this attack? The motive was a false information widely spread on the social media outlets such as 4chan, 8chan, and Twitter, claiming that this pizza shop was the base for a pedophile sex ring involving Hillary Clinton and members of her campaign. So Edgar later told police that he had planned to self-investigate the conspiracy theory. Edgar actually saw himself as a potential hero of the story, a rescuer of children. So in his mind, his motives were noble, so to speak. So the examples of attacks initiated by the false information are numerous. So let's unpack what enabled this attack to happen. First of all, we have an initial false information that has been spread by the members of alt-right. We have a susceptible individual, and this information probably enforced his existing beliefs. We also have the medium, so because the speed the information reaches their internet audiences is unprecedented. If Edgar did not have a Twitter account, he might not even hear of the conspiracy theory. And finally, we have a supportive environment. With relatively high level of confirmation bias, he could easily find the like-minded peers who would confirm his beliefs and support his actions. So a single person committing an extreme action is a tip of the iceberg. And for one perpetrator, there are hundreds ready to do the same, and thousands, if not millions, that support and justify the action. So we can see that such a seemingly silly belief can become dangerous. There are, however, more elaborate efforts to disinform and distort the public communication. Active measures is a name for a specific type of political warfare that includes offensive programs such as disinformation, propaganda, etc. And active measures and similar activities of individuals and governments are well-known tactics. For example, in the 80s, KGB has run an elaborate disinformation campaign to plant the idea that the AIDS has been invented in the US as a biological weapon. So this information has been planted in various English newspapers, mostly in India, and later in Eastern Germany with the help of Stasi. So it took a couple of years to get picked up by the mainstream media across the world. And it eventually had reached the US population and actually left consequences to this day. For example, in 1992, 15% of Americans consider it definitely or probably true that the AIDS virus was created deliberately in a government lab. And in 2005, more recently, a study by the Oregon State University revealed that over 25% of African Americans believed AIDS was a product of a government lab. So we know this saying, a lie can travel halfway around the world while the truth is putting on the shoes. So this quote is usually attributed to the writer, Mark Twain. However, there is a reason to doubt that Mark Twain ever said this at all. So thus, ironically, proving the point. So considering the level of connectivity and the openness of the online public forums, we are facing threats that can affect public health, public safety, and finally, national security. And to counter some of those threats, we must understand, first, the principles behind information spread. What are the dynamics of human online interactions? We need to understand drivers of human susceptibility. And finally, to understand and identify vulnerable groups. So let's talk about the large-scale social media manipulation. You might notice this Venn diagram on the slides during the presentation, and it kind of represents my research paradigm. So this Venn diagram illustrates the various scales of online social network analysis that I work on. We have a macroscopic scale that's mostly population analysis, large-scale social media manipulation, etc., and mostly aggregate behavior. On mesoscopic scale, we have community analysis, subpopulations, etc. And on this is mesoscopic and microscopic scale, it's pertaining to individual behavior, small-scale networks, and teams. So all the topics I research can be placed somewhere on this Venn diagram. And of course, large-scale social media manipulation falls on top macroscopic behavior. And as I illustrated in the introduction, identifying and modeling the spread of misinformation and deception is a part of my research. So a great example of large-scale social media manipulation is visible in some very recent events from the US history. 2020 US presidential election and the campaigns around it were an extremely fertile ground for all sorts of large-scale media manipulation. But this topic is actually very broad, so we focus on two main signatures of manipulation in our research. One of which is automation. That is the evidence for adoption of automated accounts. And other words, those are bots. And the second one is distortion of salient narratives with injection of inaccurate information, conspiracies, or rumors. So for that goal, we got a lot of data. We analyzed more than 240 million tweets that are collected between June and September 2020 with more than 10 million users. And we also measured certain characteristics of human behavior, such as we have a bottometer score that's a likelihood that the account is automated. We also have users' political bias, and it's calculated as the most likely users' political leaning based on their media diet. And finally, we have a conspiracy bias. That is the likelihood that the user endorsed some of the debunked conspiracy theories, such as QAnon or Pizzagate. And here are some excerpts from our results. And this upper panel illustrates the number of conspiratory and non-conspiratory users for all the political affiliations. And we can see that almost a quarter of users who endorse predominantly right-leaning media platforms are likely to engage in sharing conspiratory narratives. And out of all users who endorse left-leaning media, less than 2% are likely to share conspiratory narratives. So it's not surprising. We know that, and that's what we and others reported previously. So what is new is that we confirm the impact of hyper-partisan news outlets in disseminating conspiratorial content and at the same time attracting the automated accounts. Almost quarter of the accounts that share far-right content are most likely automated. And also far-right audience is also very prone to conspiratory narratives. And that is much more extreme than what we would expect during the period before election. So such high discrepancy in perception of reality is a sign of a highly polarized society. And that's actually a worrying sign. So this is a sample of a Twitter communication with a couple of thousand users from one of our data sets. So the nodes here are the users. And the edges are created between the users who retweeted each other. So here, the clusters that are clearly visible are created entirely using topological information, so just the connection. So when we estimate the most likely political leaning of a person based on their media bias and appropriately color them, you can probably guess what we get. So we get something like this. So we see a clear division between blue and red Twitter. And we clearly see two Twitters. And that's the mirror of the American society, highly polarized and partisan. And with such a large polarization of society combined with relatively high stakes when it comes to election, there is high motivation for various sorts of manipulation and influences. And actually, when you zoom in, like those dots are humans. They decide who are they going to connect to. So social connections that facilitate the sharing of ideas are initiated and created by humans. So those are individuals that make their own decision at a specific point in time. So just imagine if we could, given enough information, be able to model human decision process and simulate their actions over time on individual level. So let's say by simulating each user in many time steps, can we actually reconstruct such an aggregate behavior atomically? And let me tell you a little bit about our effort actually to simulate online social networks on a large scale. So to see if simulating social networks accurately and at scale is possible, DARPA devised a series of challenges. So the goal is to develop technologies for high fidelity simulation of spread and evolution of online information, while at the same time actually rigorously testing and measuring simulation accuracy. For example, this illustration shows multiple social networks with individuals, and there has been some information introduced here. So can we simulate the spread of a particular information through this social network? And can we simulate actually the spread of this information across the networks? So the main goal of the challenges is to test the current abilities to accurately simulate information spread and information evolution through social networks. So DARPA organized several challenges in order to pursue those questions. How those challenges look like? It is like a competition between multiple teams, and the teams compete who can most accurately simulate the spread of information in social networks using real-world data. So there is usually a topic around which challenge is organized. And I will show you one of those. So one of several challenges that have been working on is the challenge with a topic of Venezuelan presidential crisis in 2019. So not to go too much into details, but that was the crisis that was caused by the disputed results of the presidential election, where there were two candidates, each claiming that they are the legitimate president. So the crisis went along with protests, international sanctions, blackouts, and an attempt at a military coup in a matter of months. So it naturally caused a polarization in society and a very active attempts to spread the specific pieces of information on online social channels. So given the sufficient training data, can we accurately simulate the spread of various narratives across 3 social networks? And we have Twitter, we have Reddit, and YouTube. So the challenge is divided in the following way. We've been provided the training data, and that is training data between November 2018 and January 2019, and from that training period. And training data is all relevant data from Twitter, Reddit, and YouTube that is related to the Venezuelan presidential crisis, and mostly in Spanish. So then, the teams who participate in the challenge simulate the state of the network during the testing period. So that's in future. So the challenge is actually to simulate every action of each user from the training dataset during the testing period, including simulating even new users. So the focus is actually on simulating the information spread and information evolution on particular social network. Later, this simulation output is compared with the ground truth that at a time we don't have. So, and it's compared with on dozens of metrics. So this is our simulation principle. This is how we design our simulation. So this is very simplified representation of our simulation engine. It's actually very elaborate system that actually allows large-scale distributed simulation. But the principle is the following. So each agent here in the simulation represents a user in a social network. And there is a queue. So we built some activation models that we developed, and activation model tells agent when to activate. When the agent is active, it means that it has to do something, like a post, a tweet, comment on Reddit, or something else. Then our decision models come to play, and the decision models will tell agents actually what to do. So we have this kind of 2 main groups of models: activation models that will answer when to activate, and decision models that will actually tell what to do. So the idea is actually to build these artificial agents that would behave like humans in the artificial social network. And each agent has its own preferences like humans, also has desires as humans and communities. So the main component of this simulation is actually the decision model. And that is kind of like a brain of an agent. It will make a decision if an agent is going to make an action and where. So I'm going to tell you more about one of the decision models we used. So we actually build models for each platform, separate models for Reddit, for Twitter, and YouTube. And for each platform, we build the models that, as an input, take the features of something that the user is going to interact with. And in this case, we call it resource. So in this case, it's a post or comment on Reddit and features of a user. And that model, this is a model, this small brain, will make a decision if this user is going to is going to comment on this post. So it's going to kind of, for each action, a decision process is actually translated into a binary classification problem. And then we build the similar models for each platform. We actually build this feature vector by simply concatenating the features of a resource, user, and some mutual features. And then we build a classifier that will say if the particular action is likely to happen or not. So here's an example how we build that model of a Reddit decision model. So this is on Reddit. Similarly, it's similar for Twitter and YouTube. So we have some training data set. This is how it looks like. It's like a fairly known for anybody who deals with machine learning. So we have user features, and user features are mostly some preference features that are mostly kind of embedded representations of the topic preferences from the user's past. Then we have post features, because on Reddit, users comment on posts. And those are mostly embedded vectors of keywords, subreddits, and domains that are related to the post, including also other features of the post. And we have finally combined features. Those are features that are made by combining user features and post features. And there are some sort of distances between them. It's a distance between the user desires and post topic, for example. And this way we kind of quantify the similarity between the given post and the user's interests in the past. And finally, we have a target variable. So it will be 1 if a user commented on this post, and it will be 0 if user did not comment on this post. Okay. So given this training data set, we build a model here. And during the simulation process, user has been presented with a subset of posts. And the simulation has to decide kind of to pick one to comment on. So during the simulation, the simulator will actually concatenate the corresponding set of features and calculate the probability of interaction that had been learned previously from the training data. So it will go through all post candidates and find one actually that's most likely to be commented on. And then when it finds one, the simulator will register that as a comment on that post. So in a typical classification problem, ideally, so you want to have positive and negative examples. So the problem with this data set is that we have been given only positive examples. So we actually have a data set of what users did. But so we know what they did, but we don't know what they did not do, because we don't have an insight into users' interface. Because when users scroll, I don't know, Twitter or Reddit, they ignore many things, but interact just with some that they like. So the data on real negatives was not available to us. So we had to find a way how to solve it. We had to, what we did is actually we generate user post encounters that did not happen. And they've been marked as unlabeled. So some of those encounters are plausible and some of them are not, but we don't know that yet. So we have to first we have to label them. So to label them, we use a process called PU learning. Other words, positive unlabeled learning. And it is a iterative process where we learn the boundary around the plausible matches and label the points outside of the boundary as negative. Then that's the way how we get the proper training data to train our classifiers. So it seems that this approach worked well because it led us to win both of the first 2 DARPA challenges. We competed against 6 other teams. So here's just an illustration of some networks created by our simulation. So this is the network between the user and a specific piece of information they interacted with. So this is our simulation. This is, again, just a sample of a network. This is our simulation. This is ground truth, and this is a baseline. So our simulation actually performs well in properly identifying the sizes of clusters. And just on the first look, it looks very similar to the ground truth compared to the baseline that looks very different. And so we were able to properly identify the most important topics and the people who are going to interact with a specific topic. So the goal here was not to validate the veracity of information shared, but rather to capture the trends and model the information spreading in general. This approach can be equally successful in identifying specific pieces of information that can be misleading or dangerous. But just a sanity check that our models perform well, because it could be the case just other 6 teams happen to be worse than us by chance. So this is a small subset of metrics that is used to estimate the accuracy of the simulation. So here, these are our models, and we want our models to perform better than random model, of course, and even better than the base model that is actually a strong probabilistic baseline. And our models actually routinely outperform random and baseline model for the variety of metrics. For example, audience metrics measure how accurately our simulation predicts the audience of a specific piece of information. Similarly, share metrics are focused on measuring how well we predicted the spread of specific piece of information. And finally, we have this set of speed metrics estimate how fast the information has been spreading. So all the metrics here have been derived as a comparison to the ground truth. So our approach can accurately simulate the spread of information on online social networks on a user level. So here we actually successfully predict the information evolution for all types of information, regardless if that is legitimate or misleading information. So this approach actually can be used specifically to simulate any type of content, whether it is true or false. And Starboard actually showed that disinformation campaigns are often kickstarted by a group of coordinated actors. In other words, disinformation is a collaborative work. And usually there is a team of people that creates and deliberately shares this information. And they're organized either independently or by a nation state. And in our previous approach, we did not explicitly model small coordinated groups or teams that operate under common agenda. So then we ask some questions, like how people collaborate online to create disinformation, and how is the quantity of created disinformation related to the size of a team? So there are significant challenges in answering those questions directly, mostly because we don't have data about the collaboration of disinformation creators. So to answer those questions, we shift our focus and try to answer more general questions and build the models that later can be transferred to the specific domain. So instead of how people collaborate online to create disinformation, we ask how people collaborate online to create content. Instead of how is quantity of created disinformation related to the size of a team, we ask how is the quantity of created content related to the size of a team? Because we could have the data to estimate that. That is why we focus on understanding the collaboration patterns in small-scale networks. A convenient environment for exploring these effects of group size on individual behavior are the platforms that facilitate the human collaboration in form of the teams in various sizes. And we found 2 platforms like that. So to answer those questions, how is the quantity of created content related to the size of a team? And the second question, do individuals contribute more to larger teams? We use 2 data sets. One is, they are very convenient because we have people that work in teams in those data sets. So we have GitHub with more than 2 million users and 4.7 million projects. And we also have Wikipedia dataset with it's a sample with 700,000 users and 2.6 million projects. So this is a plot of an average work plotted against the team size. And in GitHub, in case of GitHub, the average the work is actually a number of pushes they do on a repository. So in average work is an average number of pushes of this team. So we get something like this. And we actually find a superlinear increase in productivity. So each additional collaborator increases the average group productivity. So however, notice that such a scaling factor indicates a decreasing marginal productivity of performance for increasing number of team size. It means that at the beginning, when a team size is smaller, adding additional collaborator will increase the average work of a team. However, after team size reaches a certain point, that marginal benefit is negligible. And it's similar we find similar things for Wikipedia. So in average, larger teams produce more per team member. However, users differ significantly, and it could happen that maybe larger projects actually attract more productive people. So that's why larger projects produce better, or more popular projects attract better coders and editors, etc. So to correct for those variables, we actually shift our focus to individuals. And we exploit the fact that many users work on multiple projects simultaneously. So we observe one person that works in teams of different sizes. And then we model the work of the individuals using the team size as the independent variable. So we use linear mixed effect models that are very good for regression analysis when working with studies when we have multiple observations that are made on each subject. And that's a case here because we have multiple observations that are made on each user. And linear mixed effect models actually can better estimate the effect on a group level, and in this case, on an individual level. We also correct for many multiple confounders, for example, popularity of a project, number of forks, number of watchers, repository age, etc. So also, linear models cannot be used to explain possible non-linear trends, right? So, and we have the reason to believe that there are some non-linear forces in play. So to capture this kind of non-linearity in the contribution, we perform multiple linear models, multiple linear analysis for various limited ranges of team sizes. So we built some sort of overlay of several linear models to build a non-linear model. And finally, we get this kind of unified model. It's a non-linear model for a user who makes one unit of work in a solo team. And we can see, in the case of GitHub, a user who makes one unit of work in a solo team, if we move that user to the team of 5 people, they will most likely, in average, make 20 units of work. However, for larger team size, that kind of marginal benefit diminishes. Because it could be that user also hits their kind of productivity limit. So this analysis can be used, obviously, for identifying the optimal number of members in a team. It can be used, however, for better understanding of some processes that are influenced by a number of close connections. It can also help answer the questions such as, what is the relative impact of small coordinated groups? And you will notice that this is also one of those problems where we move a bit away from machine learning and enter the realm of human learning. So in this case, the goal was to build a model that can be interpretable and potentially useful in human decisions. So for example, if a team needs, can make a decision if a team needs another computer scientist or not. So actually, productivity of a group is often the result of increased productivity of many individual members. And marginal benefit from each additional collaborator is super linear. And also people are more productive in larger groups. And this opened a lot of questions for future research. Can we actually explicitly model this information creation by highly coordinated groups of humans and machines? So understanding the small group interactions can be useful in identifying small groups of individuals that are particularly active. So we've been talking about small groups. Let's just zoom out a little bit and talk about the macroscopic temporal patterns. So we asked the following questions. How does this information become popular online? And is it possible to spread this information in a steady and disciplined fashion? So to answer those questions, we first started observing not only this information, but the phenomenon of popularity more in general. So if we understand the temporal properties of popularity in general, we can transfer that knowledge for a specific domain of this information. So we asked the following questions. So how is popularity gained online? And is it possible to acquire popularity in a steady and disciplined fashion? And what are other temporal characteristics that can unveil the popularity of online content? While performing large-scale simulations using the atomic microscopic level agents, we realized it is hard to model the popularity of salient narratives, especially different types of popularities. For example, we can have a false information that becomes viral, and that is a sudden spike in popularity. Other information can become popular gradually, such as some conspiracy theory or an idea that is brewing for a while and gradually gaining the popularity. So we realize there are versions of popularity and we miss the proper method to capture it. That is why we develop a model to properly identify different types of popularity. So a common way to approach it is by univariate time series clustering, when a content, idea, or a piece of information has been observed in aggregate. However, the online entities are usually described by multiple variables. A piece of information can have different temporal patterns in different populations. For example, some piece of information can spread differently among the populations of different ages. So observing it in aggregate could be misleading. Furthermore, a content can be described by multiple measures that are all temporal. So we usually learn a little just by observing the aggregate data. So that's why we need to disaggregate the signals into multiple parallel signals. And there are the existing methods, of course, to cluster the time series data based on its shape. However, those methods are made to work with univariate data, often ignoring other aspects of the content that are trying to cluster. So actually, we aim at finding temporal patterns of popular online content in a multifaceted manner. So we created a multidimensional, shape-based time series clustering algorithm that is able to cluster the entities based on the multiple time series signatures. So this is an attempt to build a model to capture trending topics that spread differently based on population or geography. And it can be also used to look for all kinds of information, including false information or conspiracies. So this is how we build our model. So we build on top of the existing method for univariate team clustering. It's called K-spectral centroid. It is a iterative K-means based time series clustering algorithm. And that algorithm is well known. It's iteratively assigns time series data to clusters and update cluster centroids until no more updates are made. And it actually uses a typical k-means principle. So it actually also adopts a scale and shifty variant distance function to measure the proximity of two time series. So therefore, each cluster centroid actually represents the average shape of its members. However, to make it suitable for multivariate clustering, we have to introduce a new distance function. So we actually devise a method to calculate the distance of those kind of multidimensional time series to a centroid. And actually, it keeps the scaling parameter unique for each dimension, because we assume that even if each dimension may experience trends in different scales, they should have the same temporal order. They happen at the same time. They start at the same time, they end at the same time. And we also introduce a new averaging function. We kind of extend it. And the role of the averaging function is to find the suitable centroid for each cluster. So we solve it as a version of a sort of weighted distance function between the centroid and all temporal dimensions. And finally, we introduce a deep dist iterative strategy to find the optimal number of clusters. And finally, that's our DeepM-SC algorithm for clustering. So this is the performance of our algorithm on a synthetic data set. On a synthetic data set, we know the labels. So on the left, actually the number of clusters is known, and on the right, the number of clusters is unknown. And the blue line here represents the performance of our algorithm when the numbers of clusters, here the number of clusters is given. So our method actually routinely outperforms better, like 20% better than the rival model. It also demonstrates 3 to 4-fold better performance to some other clustering methods on this particular task. So we can use this method to identify various types of information based on the way they gain the popularity. So later, when used on the real data, we were able actually to clearly distinguish patterns of popularity. And based on this multivariate temporal dynamics, we were able to distinguish different sets of topics that are clearly different in its nature and its stance. But this model can identify temporal signatures of information. In the future, it can be used to identify coordinated efforts to disinform, as well as other types of coordinated activities. So it can help identify coordinated campaigns and disinformation that has been pushed artificially, for example. So this is very recent, and it is now available on GitHub. So you can download it and start clustering your temporal data now. So due to the time limit, I couldn't get to talk more about other relevant research that has been published or it's under review. So I follow actually roughly 2 tracks of research, one pertaining to networks and manipulation, and the second one is related to team science and communities. So this is some of the research that I couldn't speak about. So it's we developed a new network embedding method for modeling positive and negative interactions in social networks. We also built the models to detect pump and dump frauds from social media signals. And I would just like to mention that this ongoing collaboration with Stanford University and Harvard folks resulted already in a paper that has been just submitted. And we are working actually on the extension of this paper, and we are very eager to publish it soon to the world. The second research track is also related to the team science and communities. And I'm kind of very proud that my most recent paper just got accepted in a journal of medical internet research, and that's my first paper in a medical journal. So what is my vision for the future? So I have identified two main topics that are important now and appear to remain relevant in the foreseeable future. One of which is public health, with a variety of important open topics. So in the immediate future, I will be working on the project I initiated and got awarded by Keston and ISI Exploratory Research Award. It's about identifying populations susceptible to anti-science that will help also estimating the levels of vaccine hesitancy. And the second one is the project proposal in making about the real-time and long-term tracker of public complacency and epidemiological measures. So this is deliberately long-term, as we have to be ready for the future breakouts and ultimately building the systems for monitoring and modeling as a part of the preparation for the inevitable next pandemic. And another topic is public and cyber safety. So my interests are focused on multiple related problems, and we are already pursuing the opportunities under DARPA INCAS program, where we observe the susceptibility to influence. And more specifically, we propose a solution to study complex interplay between the individual and the network dynamics that model the susceptibility to influence. And we also have this DARPA social cyber opportunity to explore capabilities of and to detect and counteract cyber social operations that may target open source developer communities. And finally, there is another project proposal in making that is related to early detection of coordinated disinformation attacks. Okay, and thank you, everybody. I hope I finished on time. I have also special thanks to my collaborators and students that nothing of this would be possible without them. Thank you.
Thank you very much, Goran. Actually, the time is perfect. I think there was a slight malfunction in opening the chat, so it might be possible that people might have not been able to post questions now. So we have about 10 minutes for Q&A. Any questions, either write it in the chat or if possible, let's allow unmuting and so that anyone can ask questions.
Hey, Goran, this is Craig. I have a very general question for you, which is, where do you want to go in terms of research? You know, what's next? What do you think are the important problems to focus on?
Well, as I already said, I have this kind of, actually, I was very interested in cyber safety and cyber security and previously, but when this kind of pandemic started, I also got very interested in public health and how we can help. So I would in future pursue those two tracks that include both public safety and security and online safety, online and using online networks, and as well focusing on public health and how we can help in that domain.
Okay, great. And then I have another sort of more specific technical question, which is that it was interesting that you have 3 different models for each of the different platforms. But is there any carryover across the different platforms? I mean, could you actually learn a model in one platform, and if you had the same users in different platform, use that to predict what happens in the other platforms? Or is it just that there's something different, intrinsically different about the different platforms that would never work?
So there are very many differences between the platforms. Sometimes users are the same. So the platforms differ in different domains. So they differ temporally, for example. So we have a GitHub platform that's very slow. And we have a Twitter platform that's very fast. We have Reddit platform that's somewhere in between. So we could not directly kind of use the same models. They could be, because the temporal things are very different and we use a lot of temporal features. We also match users. We match users from one platform to another. However, that matching proved to be very bad because we could match just a very small fraction of users. And so at the end, we decided actually to build models for each platform independently. And also for some platforms, we have very little data, for example, for YouTube. And some models might work on YouTube and not work on Reddit, for example, where we have a lot of data. So we started with the idea that we can build a one uniform model that will work for everything. But in practice, it didn't prove well. So we actually started building separate models, and it's not just one model for each platform. So for each platform, there are many models for separate for different types of activities that users can make.
Okay, thanks.
Thank you, Craig. Any other questions? The chat is open, by the way, right now.
Hey, this is Jim Blythe. I guess I have a related question. So Goran, talking about the agent architecture and the machine learning work you did, I like that your approach is looking at these three different levels, macro, micro, and meso. As an architect of the agent architecture, I saw a lot of different pieces of information coming together, and you talked well about learning at the micro level, so learning about individual behaviors and how that contributed to some of our performance. Would you want to talk about what could be there or what is there in terms of machine learning that takes place at the macro and meso levels? How that could be integrated? Would it be integrated with the rest of the system, or would it compete with it?
Sure. Yeah, of course, I had very limited time, and we could actually make a seminar just about the simulations. So we do have some macro level models, because we don't not just observe Reddit or those platforms independently. We get some additional data, and the data is called exogenous data. Data comes from news sources, for example, of some other sources. And we build those macro level models that actually kind of inform the simulator when to, those macro level models are pretty much involved in this. Let me just find the slide. Okay, so macro level models are used for activation models mostly. So we use some news aggregators, and we have some information. Okay, something is becoming popular, and there are some spikes. We should kind of predict some kind of spike of activity. That's when we take that news aggregators, and we say, when we introduce it into activation models, and activation models will actually tell the agents when to activate. And if there is something going on in the world, it will activate more agents at that point. And then we have more events at that time. So this is regarding the macro level models that we actually use. We also have some meso level models, because we organized also kind of clusters of users. We use different techniques to model users' coordinated activities, etc. So this is just a small, very, very small, but also important fraction of what we did in the simulations.
Thanks.
Goran, there is a question in chat by Jay Pujara. So actually 2 parts question. So the first part is, how do your findings relate to sociological results on optimal group size? And the follow-up question is, do you have thoughts about models of group substructure that manifest in large groups?
Let me just, okay, so what is the first question? Okay. So how do our findings relate to sociological results on optimal group size? So, well, there are 2 kind of schools about the group size. Some people say that actually when having a large group, people slack a lot. And then increasing the group size, everybody's starting working less. And you have a couple of super performing individuals. And then some other schools of thought say, okay, when there's a group size larger, people work more. So at the end, it ends to the matter of domain. So it depends on which domain, actually. So in the domain that we explored, it's mostly kind of open source development stuff. We found that actually the group size is beneficial. So the larger the group, the people work more. However, and it's also on the individual level. So users, the person A will work more in average in a larger team, and that's how it's. Those are our findings there, and do we have thoughts about models of group substructure that manifest in large groups? I mean, we did build some models during our simulations about the kind of communities and groups, but we did not do groups within the groups. I don't know. I mean, I could think about it, but not. I have no idea right now how we can build it.
Are there any other questions? If you have any other questions, feel free to unmute yourself. Otherwise, we are on top of the hour. Okay, I guess no more questions. Thank you very much, Goran, and everyone in attendance. And have a good rest of the day.
Thank you.